based on that, implement a policy that that can be far more flexible than let's say username based or user ID based or file permission based policy. Yeah.
This monitoring process we need to have root permission. Yes?
No.
No?
No. So what we said last time is that if so again, in the original design of ptrace, the only requirement was that A and B belong to the same user, right? And so more recently, what has been done is that if B is a child or a descendant of A, right? So if A forked and created this B as a child, then it won't need a root permission. Okay.
Okay.
But if they have no parent-child relationship, then the operating system wants you to have root permission. Right? This is why, again, when you start GDB normally, you don't have to have root permission, right? So when you want GDB to attach to an existing, an already running process, then you need root permission because the kernel. Yeah.
So just use the homework as an example.
Yeah.
You could use the drivers as a monitoring program for Vuln because it's making this a sub-process, right?
So yes. So if you could take your driver program and use it to the driver program can use ptrace attached to the vulnerable program because it is creating the vulnerable program as a child. Yeah. So this issue of race conditions is one problem. The other problem in the example I gave you is, you can check whether the file name starts with, /tmp. But what if, we talked about symbolic links. So a symbolic link could be created that links this to some other file, right? And so checking this in the monitoring process is again not that easy, right? You can there are functions to try to resolve symbolic links, but again, if the process monitoring process tries to do that, then that creates more window for a malicious process B to evade because it can change again along with the collaborator process C, it can change the mapping, and so this file name related problem is significant enough that that this kind of monitoring is not going to be the basis of something really robust, right? So maybe you can build some kind of a customized security checker for a certain application, and maybe it works well if, let's say, B is not so much a malicious process, but B is simply a vulnerable process. So you want to make sure that, okay, I have B is some is the browser process, because the browser process is exposed to everything on the internet. I want to try to sandbox it somehow, and because I'm trying to sandbox what I think is a benign process, perhaps I don't have to worry too much about all of these race condition attacks and so on, right? So that may be somewhat reasonable, but if you want to build a robust security framework, then you can't do that in the presence of all these race conditions. And so in the late 90s, people started looking at and developing this thing called Linux Security Module Framework. So the idea is that you know, let's not try to think about system calls because not everything security related, you know, happens only at the system call level, or and some of the operations, such as, you know, walking through the directory tree to resolve a name, is not an operation that you can see at the system call interface. So the idea was that, okay, instead, the way, you know, these kinds of enhanced security frameworks should be implemented is that one must go through the operating system kernel code, identify all the places where security checks are being performed, insert hooks in there so that if somebody wants to implement a more sophisticated or customized security check, then they can, you know, register to at these hooks and perform, you know, whatever checks they want to perform. Right? So you can imagine that this way of, you know, identifying all the places where security checks need to be performed and allowing a customized security monitor to, you know, register code that can run at each of these hooks is obviously a, you know, far more, you know, general approach, right? And it can be a lot more powerful. And the Linux, the SE Linux project grew out of this effort, right? So the SE Linux was built based on, you know, defining these hooks and then implementing a checker, customized checker for all of these hooks. And that customized checker, when it was put into the Linux kernel, now you call it SE Linux, right? So So SE Linux is right. So SE Linux has you know, much more a customized security policy that it enforces, and this policy is implemented using the hooks that LSM provides. Okay? And there is also another feature called POSIX capabilities that was added to Linux kernel later on, which was also you know, based on this LSM framework. So, so this is, LSM is a much more powerful framework, but it is also very complex, right? So I said, you know, system calls, you often, there are only like 20 or 30 important system calls, and the total number of system calls is about 10 times more than that, okay? Whereas the number of hooks, it's a changing number, so I don't know how many are there. I won't be surprised if there are, you know, like you know, 3,000 hooks or some enormous number, right? So it's just extremely difficult to manage. And the second problem is that unlike the system call interface, which is a pretty much static interface, right? It changes very, very slowly, right? And so if you write an application, right, that uses the system call interface, even though the operating system kernel is updated, you never have to change your application, right? Because they make sure that the interface is preserved, right? That's not how things work in the kernel, right? In the kernel, somebody will decide on a whim that they don't like the you know, the names given to some struct inside the kernel, and they'll change it, and that'll mean that anybody who, you know, uses that structure in their code has to basically go back and rewrite their or update their code, right? And this is not at all an easy task. And until recently, even vendors like VMware had a really hard time making sure that their kernel modules were up to date, right? So somebody will have to write a patch and post it on some random place on the web, and you have to go and get that in order to get your some of the VMware modules to work, right? And so this is really a big challenge, and unless there is unless you have people that are dedicated to supporting these checkers for the long term, right? It's really hard to maintain these customized security managers. And so as a result, what has happened is that there are these two applications and a few odd things that may have that have surfaced over time, but in the long run, this as a software engineering exercise, this is just too expensive to maintain and build. And so, so even though it's a very powerful framework into which an enormous amount of effort was put in, the number of applications is somewhat limited. So, so what has happened very recently is there is a new framework called eBPF. So what it stands for is there used to be BPF stands for Berkeley Packet Filter, right? And this was something that was developed in the early 90s, right? And some of you may have used a program called TCP dump.
Yeah.
So TCP dump is something that allows you to monitor network packets. You can define filters for matching which types of packets you want to monitor. And then when you get a packet that matches the filter, then you can execute some actions like printing certain fields. Right? So that's why it's called TCP dump. So you can sort of, for instance, you can monitor a particular connection and all the packets belonging to that connection, or you can, monitor all the initial connection establishing packets, and so on. Okay. So the nice thing about TCP dump or the BPF was that it allowed these filters to be defined by a user level program. Okay, but these filters would be compiled and put into the kernel, right? So therefore, it's not the case that each time a packet arrives, you give the packet to some user level process, because that will again be too expensive for the same reason as system call interception. You have a context switch for each packet, and that's not good. So what they did was they defined a language for defining these filters. There was a high-level language, and then there was also sort of like an assembly-level language. Okay, so the idea was that these high-level filters would be compiled into this assembly language, and then these assembly language filters would be put into the kernel. But obviously, random users might be defining these filters, so you want to make sure that the compiled assembly is safe. So the key effort there was to make sure that there is, so they defined an assembly language, a simplified assembly language that was safe, and before that code is loaded into the kernel, various checks are performed on it. So for instance, the assembly code cannot have loops. Okay, so you know that it's not going to run forever. The other check that is done is that it's not going to cause null pointer dereference or accessing of invalid memory, right? So these are not going to, these checks are performed, and only after that it's put into the kernel. And now you have this ability to run to run code inside the kernel space, but to eliminate all the safety and security issues. Okay, and for many years, this feature was available only for monitoring the network packets. Okay, and in the last 3-4 years, a new the facility called Enhanced BPF was developed. Okay, and now the old thing is these days called CBPF. I don't know whether it is C is for core, but I don't remember what it stands for. But eBPF is the one that. So there's been a lot of activity on eBPF in the last year or so, because again these new kernel features they get developed over time, and finally the mainline Linux maintainers have to accept and pull those changes into the mainline kernel, and then once it's gone into the mainline kernel, then people start using it, and only then the things will reach a critical point when suddenly there are a lot of people realizing that this is something that's very unique and very useful, and so I see a sudden burst of activity in the last year or two. Okay, so what eBPF allows is that instead of allowing you to simply monitor network packets, eBPF allows you to hook into a very large number of kernel functions. Okay, so eBPF allows you to hook into, for instance, system calls, right? So you can do that. But I believe let's see. Yeah, so it looks like there are tens of thousands of kernel functions, if not more, can be intercepted using this this feature, right? So instead of being limited to a few functions that receive network packets, now eBPF allows you to intercept system calls and many more kernel functions. So now, before we had eBPF, there were some other things that happened. So, for instance, there's a feature called SecComp, which was made available about 10 to 15 years back, and it started out by saying that with a very with a hard-coded containment policy, which said a process to which you apply SecComp. Right? SecComp is a system called sandboxing. Okay. So you can apply SecComp to a process on Linux, and that will mean that this process is not permitted to do, its system calls are restricted. Okay. So early on, SecComp basically said you can do only read, write, and a couple of other system calls, which are somehow basically considered very safe, right? So you can't, for instance, open a file. You cannot, obviously you cannot execute anything or fork. So anything that has the potential to, lead to unsafe behavior wouldn't be permitted. So this was a very, very strict sandbox. And over time, people said, well, this strict sandbox is so strict to be almost useless, right? Because you just cannot do anything. And so people said, okay, now instead of having a hard-coded policy that says you can only do these things, I'll allow you to say which policies you can, which system calls you're allowed to make and which system calls you're not allowed to make. Okay? And then they further generalized that to saying that you can not only say which system calls you are allowed to make, but we'll also allow you to specify checks on the argument values. Okay? But there was a key limitation, which is that if the argument happens to be a pointer, you're not allowed to. There is no provision for checking what the pointer is. So, which sort of makes this more or less, makes it nearly as useless, because what happens now is that you cannot have a policy that restricts file access. You can only say this thing is not allowed to access any files. Okay. So as a result, that's not going to be very helpful. So somewhere along eBPF came along, and what it has allowed you to do is to have a much more flexible way to tap into various operations that are being made inside the kernel, and look at not only the operations, but also look at the arguments as well. Okay, so my goal here is to sort of give you an idea of what is out there, and then let you explore them, right, as part of some of the programming assignments. Okay, so I just want to tell you what is there, and I'm not going to get into too much detail about exactly how this eBPF works. So, presumably everybody has done with the assignment. Is there anybody who's still working on the assignment? You are, okay. Well, anyway, that's not a large number, so that's good. Okay, so